All right. Hi, guys. Thanks for coming to this. I'm talking about how to do collaborative, reproducible research in H2O, and I'm going to talk a little bit about reproducible research, collaborative research more broadly, show some ways to do that, some best practices for doing that that aren't necessarily H2O specific, but I'll show examples of how to use H2O in that context, and also how to capitalize on a couple of the nice features H2O has for doing that. So really briefly, just so you know who I am, I run a company called Domino Data Lab. We make an enterprise data science platform. I'll show you a bit about that later. Before that, I built technology at a big hedge fund to do macroeconomic model development, and I've got kind of a formal background in computer science. So I want to leave you with two things today. The first is a sense of why these best practices, namely reproducibility and collaboration, are important in a data science or analytics context. And the second is much more kind of practical and concrete, some insights, tips, principles, technologies that you can actually take to help implement these and put them into practice. So on the first part, to kind of briefly motivate why I think this is important, you guys may have run into this a lot already, and so I'll go through this pretty quickly, but what we've seen is that these best practices like reproducibility and collaboration can impact the overall pace of research you're doing in a few ways. One is just raw individual productivity. People waste time reinventing the wheel, re-implementing past work, dealing with sort of environment setup because the version of packages you have installed doesn't match what your colleague has installed. People waste time digging through files like version 1, version 2, version 2 final, version 2 final really this time. You guys have all been there, I'm sure. The next sort of layer or level of impact is more about team efficiency. Overall, how does an organization get better and compound its understanding of the work that's been done? So how does one person benefit from work that another person's done without reinventing the wheel and starting from scratch? And similarly, how do people benefit from a shared context so that they sort of one part of a team or an organization knows what another part's doing? What we found is that collaboration and that shared context and that notion of compounding the work you're doing can not just speed up the pace at which things move, but also lead to more insights and spark more ideas and increase creativity. And then finally, in certain industries, there are actual regulatory requirements that make it really important to have reproducibility of the work you're doing. So insurance, pharmaceutical research, things like that. The government can actually come in and ask, hey, we need to see exactly how you did this particular thing you did. So software engineers have solved a lot of these challenges in the software engineering domain. What we've found is that a lot of those tools don't necessarily transplant well to data science work, and there are a few reasons for that. The first category of reasons are technical. Data science work, model development is more than just source code. It's also the data you use, it's the results you produce, it's the diagnostic charts and statistics you generate. And it's valuable to have all those linked together, and sort of pure source control doesn't really do it for you. Being able to track the results you produce, like the charts you generate, the models you produce, being able to do that requires that you actually run the code, run your models, run your training, run your analyses, and that opens a whole can of worms around being able to track environments that you're using, what were the versions of packages that were installed, things like that. So it's kind of a big pain to orchestrate all that and really keep that centralized and trackable. The second set of challenges is more organizational. It's that a lot of the tools that exist to do this or facilitate this kind of work are, I mean, honestly, a little too complicated for a lot of for researchers, data scientists to use. Git is very complex, even for me, and I'm a software engineer. So how do you get people in an organization to adopt things like that, especially given that it's hard to really mandate best practices top down? It's hard to tell people, you all must now use version control. Out of curiosity, and I'm going a little fast because we got a late start, these sort of technical and organization challenges and the motivation for this that I've described so far, just like, does this resonate with folks? I'd be curious if I sort of see some nods or people sort of like, yeah, they've run into these things. All right. So I was preparing this talk, and I came across this article in a Journal of Computational Biology that was just fantastic, and it's 10 simple rules for reproducible research. I totally encourage you guys to look it up. I'm not going to go through this list one by one right now. I am going to circle back to it at the end and basically show you how some of the kind of techniques and tools I've described hit on these exact items. As a preview, you can sort of let this wash over you and it'll prime you for some of what you're going to see. So the high-level strategy that I want to recommend and that we've embodied in the product we've created is to give individuals something that they want and use that to sort of incentivize people to work in a place that automatically gives them best practices. And the image here for people who have pets is sort of hiding a little pill or something for a pet in a piece of cookie dough. That's kind of how I think about this. It's hard to get people to do things that even things that are good for them. And so you need to kind of like package that in something that will provide them some instant gratification. And like I said, I'll show you some examples of kind of how we built a platform that integrates nicely with H2O to do this. But if you're thinking about how to bring this to your organization or build something similar yourself, I think this is kind of the main principle that I'd want you to take away. So fleshing that out one step further, what we found works and what we recommend, again, at sort of a principle level, is you need to give people something that incentivizes centralization. You want to get yourself out of the world where people are doing work on their own individual machines, their desktops, their laptops, because they're siloed. So how do you get people to work in a central place? How do you make it compelling for them? What we've found really gives them that value is scalable compute resources, making it easy to run a bunch of stuff at once and automatically keep it all tracked. And then also facilitating, so along with that, there's a notion of sort of managed compute environments, making it so people don't have to deal with installing packages and things. And then similarly, creating ways for easy deployment or operationalization of work, so making it easy to expose work as, expose models as APIs or as reports or as tools for non-technical stakeholders. If you can give people tools where they can then expose their work to other people without being bothered, it makes it compelling for them to put their work in a central place. So once you have things sort of in a central platform, you can capitalize on that centralization. You can do that in a couple ways. First is you can automatically track work that people are doing. You can keep it all hosted centrally so that it's shareable, searchable, discoverable, so that you can have discussion around it. And so you create this kind of central hub where code, data, results, models, the history of an analysis, the discussion are all in one place, and you haven't forced people to do things. People have kind of put it there automatically because it was good for them. One sort of aside, and then I'm going to jump into a demo. A tricky part about all this is being able to work in consistent compute environments. We talked about the challenges of reproducibility around model development and sort of running analyses, and one of those challenges is, well, what were the actual packages and everything that you installed? What was the configuration? That's hard because, or that's a pain point because if different people are working on their own machines, they can be running different versions of things, and then it's a mess to try to share work. It also can be painful if you need to really rigorously reproduce something that was done. So we've found that using Docker, I don't know how many people in this audience are familiar with Docker, but containerization and Docker in particular is a really powerful way to give people tools that can create these sort of standard, managed, consistent environments with everything you need installed, revisioned. People don't have to worry about getting things set up for them specifically. And like I said, that creates two benefits. One on the reproducibility side is that you can actually track these containers. And so if you upgrade a new version of H2O, you can actually have the record of, oh, well, these experiments I ran a month ago were running in a container that had this older specific version. The other benefit is that in these sort of containers can provide a layer of isolation that lets you try out new versions of things without interfering with everybody else. So one person can test out an idea without clobbering a shared environment for other people. So that facilitates collaboration. Okay, let me jump into some examples. And so what I want to show, I'm going to show running some H2O code using Domino, this is the platform that we've created. And along the way, I'm going to highlight a number of sort of particular techniques in the general, kind of like good principles to use, and also in the specific implementation about how we've implemented them in R and H2O. Out of curiosity, does anyone here use H2O in Python, or is this basically just sort of like an R conference in disguise? Some Python? All right, I'll show. Okay, I'll show a Python example too. So really quickly, just to orient you guys, what I'm showing you here is sort of this interface to the Domino Data Lab platform, and it's like a hub for organizing analyses. So these are all the projects that you have access to, and this is what I mean by centralization. These are searchable. People can come in, find each other's past work, find what's relevant. I know I'm going to kind of do a demo with H2O, so I can go and find the H2O project. But I could also see that my colleague had done some work in H2O as well. So if I go in here, the first thing we've got are just files. Nothing special about this. You can track any kind of file you want, scripts, data sets, results, it doesn't matter. And these files just synchronize to a folder on your computer, just the way that Git would work, or that Dropbox works, or sort of any other kind of system you're familiar with like that. So where the real power starts is when we want to be able to run experiments and keep records of what we've done. And so what the platform here is doing is it's combining, let me clean up something here, sorry. It's combining sort of easy, remember we talked about how do you incentivize people to work in a central platform? Why wouldn't they just kind of want to work on their machine? So we provide a way kind of with one click for somebody to say, oh yeah, I want to use a big machine. I want to use a 32-core machine with 240 gigs of RAM. This is all running on AWS. You can also set it up on your own on-premise cluster. So you kind of pick what hardware you want to use. And then we're going to let people just, with one command, kick off experiments to run, and we'll take care of shipping that out around a cluster, spinning up and down machines, and tracking what they do. So I'll show you what this looks like in R. You can actually interact with this system directly from the R environment, so people don't have to change the tools they're using. I can just say, I want Domino to run this script I have, and the script happens to take a parameter. You can see I've sort of exposed my, my script here to take in an optional parameter that controls what activation technique to use when we train our H2O model. I'll come back and talk through the script in a little bit more detail in a second. So I kind of say, okay, I want to kick that off. I want to run this thing. But what I could do is, this is going to go off and run somewhere on some machine. It's going to spin up, and we don't have to worry about it. What's nice is while that's going in parallel in the background is I can try another experiment, say with dropout this time, and I'll kick that off, and it's going to go get sent off to another machine. So you can see in the background here, we've got now 2 different experiments running, and if we wanted to try a version in Python 2, I happen to have kind of a Python H2O script that does basically the same thing, and so I can say I want this to run, kind of run the same thing. So I sort of submit these multiple experiments. We've got all 3 going at once. And that's great, sort of faster experimentation. But now the benefit of this from the perspective of collaboration and reproducibility is, first of all, every kind of experiment we run is tracked. And you can sort of track any results, any files that you might choose to save off. And so in this case, what we're doing is we're tracking a few things. First, we're tracking some diagnostic statistics. And I'll show you how we do that directly in R. We save a little file to disk. Let me show you what this script does, sorry. I'm still recovering a little bit from getting a late start. So this script just initializes H2O using the standard R package. It looks at this parameter we passed in for the activation type. It uploads this data set. It trains our model. And then it records some diagnostic statistics. So it prints out the performance. It actually saves that to a file, so we have a record of it. It pulls these statistics off the trained model, and it saves them in JSON to a file on disk here. We call Domino stats. So we save R squared, MSE, AUC. And we do a couple other things here. We save the model as an RDA file. We save the random seed as an RDA file. And then every time one of these experiments runs, what the Domino platform is doing is it's detecting these sort of statistics that were saved to disk, and it's also detecting any new files that were produced. And so in this case, if I view the results of one of these past experiments, we'll see, I'm going to show you more about that Java file in a second. We'll see sort of the performance stats that were written out. We'll see the, the performance plot that was produced. And then we'll also get a revisioned copy of anything we saved to this, so the model RDA file, the random seed. And what that lets me do, or lets anyone do, is really easy comparison. So I didn't have to worry about creating these copies and naming them differently or overwriting past results. It all just happened automatically under the hood. So I can take two different versions of two different activation functions I've used, and I can compare them. And I can see kind of side by side how my diagnostic statistics lined up. I can see, well, we don't know how to render a jar file. That's not interesting. But I could take a look at see how my performance differed side by side. I could take a look at how my performance plots differed side by side. And then if I wanted to get back to any past version I've produced, like I knew, say this thing I trained earlier today, late last night, I knew was really good, I can actually browse back to kind of the precise version of all my source code and results and everything that were associated with that particular experiment. So it's this notion of, kind of automatic version control of the code, the data, the results all linked together. If you were looking at any past set of results, there's a kind of a pointer back to the precise version of the experiment that ran. We know this was run number 15. If I click that link, we're taken right back to that particular record that produced it. So a couple other things that were kind of powerful that were going on under the hood here. The first is I'm taking advantage of the fact that H2O can compile models to Java or serve models as Java. And I've written a little function here that all it's doing actually is it's calling out to a shell script. But what the shell script is doing is accessing the locally running H2O server to retrieve the Java code for the model I've just trained. It's downloading it, it's compiling it as a jar, packaging that up, and then we're sort of renaming it so that we have a consistently named record of all these versions. So anyway, there's a little bit of code I hacked together actually before the talk. But in R, we can call out to that process, or we could have implemented that same thing directly in the R code. So what this means is every time we run an experiment, we run the model, we train it with R, we're also keeping a record of the Java code that represents the model. So there's that record here, as well as the final compiled jar. So this jar is now revisioned along with my history of experiments, rendering it we don't know how to render it in the browser, but I have this automatic revisioned history of all the past jars I've trained. All right. And by the way, in Python, this kind of works exactly the same way. So if we were looking at my Python code, we can save out diagnostic statistics to a JSON file. We'll track all those. You can use, I don't have it implemented here, but a technique in Python is pickling. You can save arbitrary in-memory data sets as pickle files, and then those will be kept and tracked in revision as well if you need to persist an in-memory result you've produced. So we could compare how the same activation function looked across R and Python. So here's the one I ran in Python. Here's the one I ran in R. And if I compare them, oddly enough, the diagnostic statistics look similar but a little different. So no, there might be an issue in my code, or maybe I had changed something between here. Although we can actually, we can sort of scroll down and look at a lot of files changed because that was last night. Yeah, so not much change in the input code. I added this shell script, which Python's not using. Okay. I went really fast. Do folks have questions about the code that I put up there? Okay, let me flip back to the sort of list I had for reproducibility and kind of touch on a couple things. So if we go down that list that we showed a minute ago, first thing was for every result you produce, keep track of how it was produced. And what I'm sort of advocating is a system that does that automatically, so people don't have to worry about it. It's, if you rely on people to track things, they're going to be mistakes. So, yeah, kind of what I've showed, that just happens automatically. Avoiding manual data manipulation steps, that's not something that I've shown how to make any better, although nothing I've shown makes that worse. You are sort of relying on people to codify or implement their data manipulation steps. Archiving the exact version of external programs that are used, I didn't have a demo of that, but that's actually also kind of happening automatically under the hood by leveraging Docker. And so every one of these experiments that gets run has linked to it a unique Docker container ID. And we spin up and down Docker containers, and so you can get back, if you have enough disk space, you can keep them around as long as you want and access them again. Version controlling custom scripts, that's sort of connected to the first thing that happens automatically. Recording intermediate results. So this, what I wanted to recommend here is to make use of, in R, things like RDA and RDS, which I sort of showed this briefly, but the save function in R or the pickle function in Python will just let you save any intermediate in-memory variable, or even your entire workspace, out to a file. And then that file can be tracked and revisioned even if it's a binary file. Another really neat trick in R is save image, which will actually save out all the intermediate variables in your workspace out to disk. So you can sort of do everything in one shot. And in Python, pickle is kind of the equivalent concept. For analyses that include randomness, note the underlying random seeds. There are actually a couple ways to do this. You can take advantage of the same sort of technique I showed you just now with around the save function. So you can persist. In R, you can always get the random seed by just evaluating this value. And so you can save that to disk so that you could reload it later and reproduce something even if it was random. You can also, I showed writing out, sort of storing arbitrary structured statistics as JSON. You can do that as well. You can sort of store the seed value in kind of JSON. Always storing raw data behind plots. That's another kind of the same story. Pickle, RDA, RDS. Discussions and comments, number 9, connecting textual statements to underlying results. There are a couple ways to do this, and kind of glossed over it in the interest of time, but I'll circle back. So by virtue of having results in a central place, you can facilitate discussion about them. And so you can do a couple things. You can sort of leave comments or questions about a particular experiment, like why did you try that parameter? And that can sort of notify all your collaborators on a project. There's a record kept of that. You can also leave comments or questions or discussion about specific results. This plot looks great. And what we'll do is we'll track all those comments, questions, and roll them up into sort of like a project-level news feed that preserves the context in which the comment or question was left. So I can see that I left a comment specifically on this chart. I can kind of browse back to it if I want and get right back here and reply. Or I could see that another overall question was left at the level of an entire experiment, run number 23 that I tried. So again, from my perspective, the real thing that unlocks the ability to do things like this, connect textual statements to underlying results, is to have work in a central place. There are other tools that do this really nicely. In particular, Knitter is a nice way, using R to combine textual statements with results you've produced. Or I probably don't have time to go into Knitter now. The other just kind of relevant tool I want to share here is notebooks. Jupyter Notebooks, which I don't know if you guys are familiar with, mainly grew out of work around Python. They used to be called IPython notebooks. But they also, kind of a lesser known feature is they completely support R. And so what you can do is you can work interactively in like a notebook context where you can mix code and visual results and comments and sort of markup and HTML even to create self-documenting, basically, workflows. And this is a Python example. But you can see, I can just sort of evaluate arbitrary Python snippets. I can have nice kind of comments mixed in here and then render the results really nicely in line, whether they're tables or plots or anything. And then this can also provide a place where less technical folks can easily come in and leave annotations and comments directly connected to the bit of code that was running or the result that was produced. The way this works in R, and I don't have an R example prepared, but in Jupyter Notebook, you can just start a R notebook, and here you can execute sort of any R code you would normally want to run. So if I do that and that, and this works with plotting as well. So yeah, it's pretty slick stuff. And then yeah, so anyway, works great with any R package, including H2O. So connecting textual statements to underlying results, using tools like notebooks, using tools like Knitter, or using discussion and commenting around a hosted repository of results. That was a really, really quick tour. I've got a couple minutes for questions.
So do we have questions? Well, I'll start, actually. So this actually looks like it'd be kind of... Sorry.
Voice in the ether.
This actually looks like it'd be very interesting for also educational purposes, right? So we, at H2O, we have a lot of meetups, and we have a lot of people kind of come trying to get into data science and trying to sort of learn the process. And, one of the things I saw here, I mean, it's very clear how this would work well for a group of data scientists who are collaborating within an organization, but it also seems like it'd be kind of cool for coaching and kind of working through everybody's logic on that. Has anything been approached on that? Yeah,
we work with we do work now with a number of data science training programs, but also consulting firms that do data science training for kind of corporate settings. And it's exactly what you're describing, that it's a central place that has all the execution environments already set up, so people don't have to waste time configuring and installing things. And then there's transparency into what all the different students are doing. And we've used this a lot for blog posts, actually, to promote a lot of the H2O work. So we've done a blog post that kind of highlights some things in H2O, and it's exposed as a public project. So anybody, I'll log in with sort of a Chrome incognito window here. Anyone can come and visit this page and see all these examples of kind of working H2O code that's already pre-set up to work in an environment with everything installed, and anyone can just fork this project, sort of a bit like GitHub. So you can fork this, kind of get to start working on it, make your own changes, and you don't have to worry about, again, that infrastructure, plumbing, configuration aspect of getting up and running. I can't tell you how many people we've talked to sort of like, well, there was this great code example on GitHub, but then I tried to download it and I immediately got stuck because it just doesn't run.
Cool. Yeah. Years ago, I worked on something very similar for, when people would publish a paper and it's got some obscure Fortran code, it's like, okay, well, how does somebody run that a year later?
Yeah, absolutely.
Okay, great. So I got the first question, so I get the mic, but I don't want to... Here we go.
You mentioned you use the Docker. Do you need to create your own Docker image? And if yes, and how often you have to create the Docker image for this scenario?
We have a bunch of sort of standard Docker images built in, and then we provide an interface through the platform that lets you add things to them. So our intention, our sort of goal is to give you the flexibility of Docker, but make it much easier to sort of work with and manage. Does that answer the question? Yeah. Sure. Yeah. The question was, can I talk a bit about the API? Can you just say a little bit more what you mean by that, or sort of what you were interested in?
In terms of like runtime, like if you wanted to, a lot of people have models they build that they want to deploy,
Right.
but they need to make sure they could run quickly. Some of them have to be run in real time.
Yeah.
Maybe you went over that a little bit. I came in.
No, I didn't, kind of in the interest of time, and partially also because it's a little bit overlapping with functionality that sort of H2O has built in. But we do let you, well, our functionality for kind of deploying APIs is a little bit more generic. It's language agnostic. It's not package or model dependent. So we let you take any R or Python code and expose it as an API that's sort of meant for production work. So basically, all you do is you specify a function that you've written, and it can be any function. It can do anything you want. It can use any packages, so it can use H2O, but it can use old, like more basic stuff as well. And we will translate your function into sort of basically a web service. So the inputs, the arguments that your function expects will be the arguments to the API, and the return value from your code will be the return value from the API. And all you have to do is say, my code is in a file called predict.r, and my function is called predictQuality, or whatever it's called, and you hit publish. And we'll stand that up as like I said, sort of a production-grade API with little code snippets and lots of other languages so you can interact with it. And from our perspective, this is one of those things that encourages people to come work in a central platform. It's easier for them to productionize and publish and deploy their models. But a lot of the benefit that the organization is getting is actually that this is all revision. So every time you publish a new version, you deploy a new version, we keep a record of it. It's easy to roll back to it, et cetera, et cetera. I don't know. I didn't sort of do the, yeah.
Okay, great. So if we could thank our speaker.
Thanks, guys.